So we will now give a variational characterization of the eigenvalues and eigenvectors of for a compact self-adjoint operator. So H Hilbert space, which is separable, and T in LH, compact and self-adjoint. So you have a orthonormal basis of eigenvectors. So for each eigenvector, choose a corresponding eigenvalue, and then we number the eigenvalues in decreasing order for non-negative eigenvalues and in increasing order for non-positive eigenvalues. So for the result I am going to state below. It doesn't matter where we put the eigenvalue 0, if at all it is an eigenvalue, because it will come last. So you will have that lambda, so we call them lambda 1 plus, which is greater than or equal to lambda 2 plus, greater than or equal to etc., greater than or equal to 0, and lambda 1 minus less than or equal to lambda 2 minus less than or equal to, which is less than or equal to 0. Now I put less than or equal to or greater than or equal to because they all may not be distinct eigenvalues. So if we have started with the basis of eigenvectors. For each eigenvector we have chosen an eigenvalue, and so many more than one eigenvalue vector may correspond to the same eigenvalue. So for instance, there may be an eigenvalue whose geometric multiplicity is 3. That means there will be 3 eigenvectors in the orthonormal basis which correspond to the same eigenvalue. So for instance, if lambda 2, lambda 3, lambda 4 may all be the same. Okay, so like that. So this numbering by repeating eigenvalues according to their geometric multiplicity. So if the kernel of lambda I minus t of the null space or null space of lambda I minus t say has dimension 5, then the corresponding lambda will occur 5 times consecutively in this list somewhere. Okay, and also all these need not exist all the time. For instance, you may have an operator which has only non-negative eigenvalues or only non-positive eigenvalues, or a mixture of both. Both may be infinite sets, one may be finite, and so on. So all kinds of things are happening. We are just giving you a numbering here. Okay, so ui plus is the eigenvector in the basis corresponding to lambda I plus, and ui minus is the eigenvector in the basis corresponding to lambda I minus. Okay, so these are all the eigenvalues and eigenvectors which we have. So we've set v0 is a singleton 0, and we set vm to be the span of u1 plus vm plus minus to be the span of u1 plus minus um plus minus. That means vm plus is the span of u1 plus u1 to um plus, and vm minus will be the span of u1 minus u2 minus um minus. Okay, so this is the notation which we are having. Okay, so now we have the following theorem. Okay, so let m be greater than or equal to 1, then lambda m plus will be equal to T of plus plus. I don't need the bracket here. Okay. This is also equal to the max over all V not equal to 0, V orthogonal to Vm minus 1 plus of TVV V by norm V square. And the third one is the minimum over all V contained in H, dimension V equals m minus 1, max V not equal to 0, V orthogonal to V, and then TVV by norm V square. Okay. So let us comment briefly on these things. The first one is just saying is more or less obvious, so you can we will see it in a moment. Now this TVV by norm V square for V not equal to 0, this is called the Rayleigh quotient. So we are expressing the eigenvalues as the maxima or minima of the Rayleigh quotient over some subspaces. So there is some constrained optimization problem which we are showing. That is why we call these as the variational characterization. Now the first two depend on the orthonormal basis which you have chosen. The basis can be chosen in many ways. So we are choosing something, and so this depends on that. The third one doesn't depend on any basis. Okay, so this is called the intrinsic characterization. Okay, it doesn't depend on the choice, does not depend on the choice of eigenvectors. Okay, so that is why this is called intrinsic. So it's entirely independent of its frame invariant, basis invariant. Okay, so let us try to prove this. First one is obvious. So you have TUM plus is lambda m plus UM plus. So you take the inner product. So T UM plus UM plus is equal to lambda m plus UM plus UM plus, and this is equal to 1, and therefore that's equal to lambda m plus. So that proves the first one. That's almost immediate. Okay, now let us see the first. So let V belong to H. So you have an orthonormal basis of eigenvectors, and therefore you can write V is equal to sigma over K V UK plus plus sigma over N V UN minus UN minus. I am not writing the limits because, as I said, they may be finite, infinite, they may not exist, etc. So we are just writing sigma over K, sigma over N. And so what is TV? TV will be sigma over K. You have lambda K V UK plus plus sigma over N lambda K plus, and sigma over N lambda N minus V UN minus UN minus. So then you take TVB. TVB is what? So when you take the inner product TVB, so all cross terms are going to disappear because of the orthogonality. Only the square terms are going to remain. So this will be equal to sigma over K lambda K plus mod V UK plus square plus sigma over N lambda N minus mod V UN minus square. And recall that all lambda n's are negative, and therefore this is less than or equal to sigma over k lambda k plus mod v uk plus square. Okay. So now we have v orthogonal to v m minus 1. Okay. So that means all the bases up to m minus 1, all these elements will disappear, and therefore you have TVV is less than or equal to or rather is equal to sigma k greater than or equal to m lambda k plus mod vk uk plus square. Okay. So now we have numbered the positive eigenvalues in the decreasing order. So the biggest of them will be lambda m plus, and then all the higher for the other k it will be less. So we have that this is less than or equal to, this is the biggest of them, so that is equal to lambda m plus of sigma k greater than or equal to m mod vk v not vk sorry v uk plus square, and that is less than or equal to lambda m plus norm v square. Therefore you have the TVV by norm v square is less than or equal to lambda m plus, and this is true for all the v's, and therefore in particular the sup of v not equal to 0, v orthogonal to vm minus 1 will be less than or equal to this. But um plus is also orthogonal to vm minus 1 plus and therefore, and we have the TV um plus by norm plus square is equal to lambda m plus by 1. So and therefore that is equal to lambda m plus. So there is an element here for which this is attained, and therefore you have max v not equal to 0, v orthogonal to vm minus 1 plus of TVV by norm v square equals lambda m plus. Okay, so that is the second statement which we have. Okay. So now for the third one. So let v contained in H, dimension of v equals m minus 1. Okay. Then claim there exists a u belonging to Vm plus such that u is not equal to 0 and u is orthogonal to V. Why is this 0? So we can why is this so? We can argue in two different ways. Suppose this is not true. That means u is not there is no non-zero element which is orthogonal to all of V. That means Vm plus intersection V perp, this is singleton 0. That is what we are saying. But codimension of V perp is m minus 1, because V is a m minus 1 dimensional space, and therefore you cannot have an m dimensional space completely non-intersecting with it, okay, because the codimension is only m minus 1 and we have a m dimensions. Therefore you have definitely this is a contradiction, okay. But or the other way, if you want to look at it, is that u is in the m dimensional space. So say u can be written as sigma alpha I ui plus I equals 1 to m. So you need m constants alpha i's to be determined. Now we are giving, by saying it is orthogonal to m minus 1 dimensional space, we are giving m minus 1 conditions, and therefore there is still one more condition free for you, and therefore that will help you to determine the vector u. Okay, so there will be more than one vector in fact, and therefore you always have a u which is non-zero, such that u is orthogonal to v. Okay, therefore sup of tvv by norm v square, v orthogonal to capital V, v not equal to 0, is greater than or equal to TUU by norm u square. Okay, so let us compute this TUU by norm u square. Okay, so u is alpha I ui plus, and therefore norm u square is sigma I equals 1 to m mod alpha I square. Okay, and TUU is nothing but, again similar to the calculation which we have already done, is sigma I equals 1 to m mod alpha I square lambda I plus. Now we have, again remember that we are determining the eigenvalues, numbering the eigenvalues in decreasing order, and therefore lambda 1 plus will be the biggest, lambda m plus is the last. So this is bigger than or equal to lambda m plus into sigma alpha I square, which is lambda m plus norm u square. Therefore TUU by norm u square is greater than or equal to norm u square. Therefore sup v in v, v not equal to 0 of TUU TVB by norm v square is greater than or equal to lambda m plus. Okay, and this is true for any m minus 1 dimensional space. Therefore, if you take the inf, okay, of v contained in H, dimension v equals m minus 1, this is still true. Okay, now T compact implies that sup v contain v orthogonal to v not equal to 0 TVB by norm v square is in fact attained, is in fact equal to max v contained in v not equal to 0 TVB by norm v square. Because you take a maximizing sequence, then TV will converge strongly, V will converge weakly, and therefore you will actually, the limit will be a maximizer, and therefore you will attain, and it will also be orthogonal to V, and therefore it will attain the maximum. So the sup is actually a max. And now we have already seen that max over Vm plus so we have already seen that max over V not equal to 0, V orthogonal to V m minus 1, this is m minus 1 dimensional space, TVV by norm V square is in fact equal to lambda m plus. So there is one space for which this is attained, and therefore this implies that min over all V contained in H, dimension V equals m minus 1 of the max V not equal to 0, V orthogonal to V, this always a plus, okay, is of TVV by norm V square is in fact equal to lambda m plus. Okay, so that is the third statement which we have proved. Okay, so we have proved all the three statements, and we have shown this thing. Okay, so remark, similar theorem, similar result for lambda m minus. So in fact interchange max and min. You will get the corresponding results. Okay. Now corollary of the previous result. What is lambda 1 plus? So it is the max over Vm minus 1 plus orthogonal that. So but that is m equals 1, so we have 0, and consequently you will have that it is 0 orthogonal is nothing but the whole space. So this is in fact equal to maximum over V not equal to 0, V in H TVV by norm V square. You can also see it directly from this statement here. So you have TVV is equal to this, and therefore this is less than or equal to lambda 1 plus, because that is the biggest of them all, and consequently norm V square. Okay, and then for the U1 plus you already have attained it, and therefore the maximum over the whole space is in fact. And this is a very useful thing, because you get directly a maximization problem which you want to solve for the first eigenvalue, and therefore you can find it. Okay, so we will wind up with this, and then we will do the exercises.